compared a Q6600 at the rated clock rate to an i7 quad-core processor, the i7 quad-core is easily twice as powerful, and yet it consumes about half of the power.
What do you clock that with Q6600? What do you clock that?
I just clock it at the stock speed,
Oh.
That's why it's still humming, and it's super reliable. That thing is like a tank.
You should get your clock cycles out of your space heater.
Well, because I don't understand why people have to overclock their processors either.
Just think of it as underclocked from the factory.
Yeah, well, that's how I do. I run my cars too. Could have put a turbo on it, but don't have to. All right, so we're getting past this one sentence now. In billions of, okay, so the 1 gigabyte is 1 billion locations. Okay, when we talk about locations, each location can only store a byte, because most of the computers that we use today, they are byte addressable. Okay, in other words, each address corresponds to a particular byte. Okay, so that will become useful later on. I just want to kind of mention that whenever I can. Memory can be used to store data and code, as most of you already know. In a C program, the code goes into one portion of memory, and then your your global variables goes into another section of memory, and then the stack goes to yet another section of memory. As a result, it seems to make sense to connect the ALU to memory so that an ALU can directly access the values that you need to feed the ALU, and also to store results from the output of the ALU directly back into memory. It seems to make a lot of sense. Well, there are only two problems with this approach. Okay, you can read this part here, but I can already I can give you an analogy and leave it up to you to read the rest, the details. Okay, so let's just say that I am the ALU. Okay, I'm the ALU. I have no storage capacity. So in the analogy, I'm holding a TI calculator. Okay, I'm holding a TI calculator that has no memory. Okay, so this is kind of like a stripped down calculator. Okay, it doesn't have any ability to store values. But if you tell me what to add, I can give you the sum. Okay, really quick. All right. In this analogy, what would be memory in this analogy? It's not Post-its that I have quick access to. It's not the whiteboard. It is not even your binder in your backpack, because that's way too quick for me. Memory is so slow, it would be analogous to binders that we store in the library. Okay, so every time I need to do a computation, I'm going to ask two people in the class or one person in the class to go on 2 trips to the library to give me the 2 numbers that I'm supposed to add or subtract. So I'm just going to say, hey, I need you to go to the library, the 3rd floor, which aisle, which shelf, and which binder. Get me the number on page blah blah blah. Okay, and then you will have to grab another number for me. So after, how long would it take you? If you run really, really fast.
Couple of minutes.
Couple of minutes. Okay, let's say 5 minutes. Okay, so 5 minutes later, you guys come back, and what do I do during those 5 minutes? Remember, I'm the ALU.
Wait. Twiddle your thumbs.
Yeah, I'm just twiddling my thumb, waiting and waiting. So you guys finally, eventually came back and go, these are the 2 numbers that you need. Okay, this is the answer, and I want you to go back to the library and store this number, blah, 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 blah. So another 5 minutes, you come back and say, okay, now I need to know what I'm supposed to do next. Go back to the library and fetch the next instruction. Okay, that's how things will look like when we rely on memory to store everything, because it really is that slow by comparison. Okay, so that means your 2 gigahertz processor is completely pointless, because it cannot possibly keep up with, memory cannot possibly keep up with that kind of speed. You might as well just get a 100 megahertz clock rate for the processor, because that's just how fast you can store and retrieve information. Yep.
Would the library be the cache, or?
No, the library is the main memory. So I'm bypassing. I'm not using the concept of a cache in this case. Caching is helpful, but your cache is only so big. So when you look at the cache, it is a very small portion of the entire memory. So caching works really well when you have locality. When you're executing instructions over and over again, from the same location, or when you're retrieving information from the same location, or when you store information to the same location over and over again, the cache is extremely useful. But a lot of algorithms do not work that way. So you still have to go to the library because it's not in the cache. Okay. So let's go ahead and read the physical limitations part here. The capacity of memory is huge, but that's the problem because they cannot be located in the same processor on the same die. For those who want to know why, the limitation is due to the number of transistors that we can fit into a single silicon die, and more importantly, it has to do with the routing resources on a silicon die. Routing resources refer to how many paths can we connect from one point to another point. A silicon, a piece of silicon is kind of like a circuit board. It's still a two-dimensional device. So that really makes routing difficult because you cannot really just say, oh, I want to go from this point to this point, this point to this point. If all those connections you have to cross over, it's really hard to design a circuit board to make that happen. A lot of the circuit boards that we use today, okay, you can kind of imagine this is a prop. This is a circuit board. You can kind of imagine on the surface, front surface of the circuit board, you will have traces, basically just copper, printed copper that is on the fiberglass material. You can kind of imagine on the back, there may be some different paths, and there are constructs called vias, VIA, to connect the top layer to the bottom layer. So you can actually have signals that go on this side, and then through a via, it connects to another trace on the other side. That really helps in terms of making more routing resources available, but not nearly enough to make motherboards of modern computers happen. Modern motherboards probably have 6 or 7 or 8 layers. In other words, it is sandwiched. Okay, you have the top and you have the bottom layer, and in between those you have 6 additional layers, just so that it has enough routing resources. Okay, and that's why it's hard to fix those boards, because if you have a problem within the interlayers, the intermediate layers, there's nothing you can do to fix it. Okay, but that's basically routing resources, and it's very important when you're routing silicon. As a result, memory is implemented as a separate module that is connected to the processor by copper traces, copper wires on the circuit board. Modern PCs also have a north bridge. This was written a long time ago when north bridges were still used, and these days with the i5, i3, i7 processors, they don't have a north bridge anymore. But it is still separate. There's still a physical separation of the processor from memory. Now the copper wires, the copper traces on the circuit board that connects your memory modules, your DIMMs, to the processor, there's a certain physical length, right? Okay, the physical length of the copper wire will have certain physical properties. The physical properties in this case, that is actually making things worse, is inductance and capacitance. How many people have taken the physics class, on electrical stuff? Okay, so what would inductance and capacitance do to a square wave, or supposedly square wave, going from one side of the wire to the other side of the wire?
To push charge up.
It rounds it off, right?
Yeah.
Okay. So in other words, if a signal is supposed to look like this, it's a falling edge. When it's going through copper wire, because of capacitance and also inductance, it will go like this. Okay. When it drops, it cannot drop that quickly. Okay, so the drop will be initiated here, but because of the capacitance, it cannot drop. And then it will ring here because of inductance, and then it will settle down like this. Okay, so that means we cannot really change the signal very often, because the more frequently you want to change, you try to change it, then it becomes shorter, right? And then the narrower it becomes, or the shorter amount of time you give it, then at some point the distortion is so much that you don't get the signal anymore. The other side doesn't understand, is that a 1 or a 0 or something in between. It can no longer see this is definitely a 1 or this is definitely a 0. Okay? And this is physics. I mean, there's no way to defeat it as long as you have a copper wire of a certain length. So these physical properties can delay signal change from one end of the copper wire to the other end. And that's why you really can only do so much to speed up the speed of a memory bus because of this. As a result, there's a limitation of how quickly we can move data from one end to and from memory, relative to the processor. There's a side note related to the terminology. Modern PC memory is DDR2, so you can kind of imagine how long ago I wrote this. It is DDR3 now.
DDR5.
Is it DDR5? But it doesn't matter what DDR we are talking about. DDR is only useful when you're accessing memory in burst mode. Okay. In other words, if you're accessing not just a single location, instead you're accessing, let's say, 128 locations, then DDR is going to help. Okay. Because instead of telling you to go get one number from one single page, I'm telling you just give me the entire page, okay? Because I will need all those numbers on the entire page. So now I'm saving you a lot of trips, right? Because depending on how big a page is and how many numbers are on that page, I'm saving you all that time that you would otherwise have to go, okay, I'm grabbing the next byte, the next byte, the next byte, the next byte, and each byte takes a full round trip. But now, only one trip, and you can grab me all the other bytes. Not quite like that, but that's the general idea. Okay, the DDR technology is only helpful when you're doing burst mode access. So you just kind of read through this whole thing, and then the summary is probably still true, even though we have DDR5 memory, and because guess what? The processors are also getting faster. Okay, when I wrote this, a quad-core processor was like, wow, that's really high tech and lots of processing power. The Q6600 was, wow, I wish my gaming computer had that. Okay. Would you play on a Q6600 computer these days? No, right? Okay. So that means the race between your processor speed and memory speed is still on, because memory speed is faster, but guess what? Processor speed is also getting faster. So we are still encountering the same problem, because the ALU can execute instructions or perform calculations at about 10 times the speed you can actually get stuff from memory and store things back into memory. So the problem is still there, even though we are not using DDR2 anymore, but the processor is also getting a whole lot faster. A kind of connected problem, or connected thing to all this discussion is, back then the Q6600 has the highest number of cores on a single chip. How many cores can we fit onto a single chip these days?
12.
Was it 12?
Well, it's 6 cores with hyperthreading.
Okay, so it's really that's technically 6 cores or 6 processors, but the number is going to increase. Okay, and how many processors can you fit on a single motherboard in a server? Some of those can fit 4. So you can have each processor has 6 cores and they have 4 processors. So you can have up to 24 cores running concurrently, not even counting hyperthreading. Okay, but they all connect to the same memory bus. So you still have contention, when it comes to accessing memory. Yep.
I heard the